So once you know how to do some basic separation of variables, it actually opens the door to being able to do some complete FRQs that you could see on the AP Calculus test. This FRQ is from the 2016 test. It's from the AB test, and it's question number 4. So let's look at what they ask us to do. They ask us to sketch the slope field at these 6 points where there are dots, so it's not too many points. They then ask me they tell me y is equals f of x is a particular solution to the differential equation with these initial conditions. So that's an x, that's a y. And then they ask me to find the tangent line. Now be careful, it's a tangent line. And then for this one, part C, they asked me to actually find the particular solution to the differential equation with those same initial conditions, 2, 3. So let's start with part A. All right, so what I need to do is sketch this slope field. So I need to look at all these coordinates and then plug the values in and get the slope at each of them. So this is 0, 0, this first one, and dy dx evaluated at 0, 0. You don't have to show this much work, but it doesn't hurt to. But when I do it at 0, 0, I got a 0 in the top, right? So that makes it 0 overall. So I get a flat slope. And you should see that actually that this 0, 2 is going to give me that same value. So I get a flat slope there. Now this is 0, 1. So I'll do dy dx evaluated at 0, 1. And that's going to be 1 squared, which is 1, over 0 minus 1, negative 1. So that's the slope of negative 1. So I can draw this line as if it connects to this one over here. I can do it for dy dx evaluated at 2, 1, which is going to be this point right here. And that is 1 squared again over 1, and then 2 minus 1 gives me 1, so this has a slope of 1. Remember, I'm going to draw it as a slope of 1 so that it would, if I were to continue this on, it would hit that. So maybe it needs to be a little less steep. So it'll hit there. And then the next two, dy dx evaluated at 0, 2 is going to be 4 over, because that's 2 squared, negative 1. So that's a slope of negative 4. So this is just going to be like really steep. Imagine it hitting a point down here if I extend it out far enough. And then when you calculate the other slope, you're going to get a positive 4 as well. So there we go. We got part A done. Boom. So let's move on to part B. All right, they say tangent line. They want the equation of the tangent line. So whenever you see tangent line, there's always something I ask you to think of. So part B, I'll do it right here, and then I'll do the other one down below. I like to think of y minus y1 equals m times x minus x1. That's point slope. So what do we know? Well, we know that x1 is 2. I'll write that here. And then I know that it goes through the point f of 2, 3, right? So that means x is 2, y is 3. So that means y1 is 3. So now all I have to do is figure out the m. How am I going to figure out the m? Well, remember, this differential equation up here is the slope. And it's the slope based on x and y. So I can do dy dx evaluated at 2, 3. Sometimes when I'm doing this, it'll be one of the ones that I found over here, but it's not. You can see I didn't do 2, 3 up there, so I got to plug it in. So that's going to give me 3 squared. Remember, I'm going off of the formula dy dx equals y squared over x minus 1. So I get 3 squared over, what's x? 2. 2 minus 1. So that gives me 9 over 1, which is just 9. So what's my point slope? It's y minus y1 is 3 equals 9 times open parentheses, x minus x1 is 2. And remember, we don't have to simplify. Point slope is good on FRQs 100% of the time. So this one is good to go. Now, before I move on to part C, I need to make sure I read the entire question. So let it be the solution, initial condition, write an equation, tangent line. Use your equation to approximate f of 2.1. So I need to make sure that I do that. I think people frequently just don't even read that and forget it. In fact, I almost just did that. So this is actually set up well for us to do that approximation. We do y minus 3 equals 9 times, we're evaluating the tangent line at 2.1. So I get 2.1 minus 2. And notice that just gives me 0.1. So I get y minus 3 equals 9 times 0.1. And honestly, you can leave it as 9 times 0.1. We can add the 3 to both sides. Y equals 3 plus 9 times 0.1. And that would be a legitimate answer in terms of AP form. But this is really easy to multiply. I can take this decimal, move it once, and this decimal, move it once, and get 3 plus 0.9, which gives me 3.9. So that is part B. Now let's go on to part C. So this says find the particular solution y equals f of x to the differential equation above, which I have written right here, with these initial conditions. So remember, particular solution is the one that goes to a point where we've solved for C. This right here is how we're going to solve for the C. And then you should know at this point, because of what we've been talking about, what method I use to do this integration. I use separation of variables. So we'll go ahead and get started with that. I get dy over y squared because I divide by y squared. And then I'm going to multiply by the dx equals dx in the top over x minus 1. I multiplied by this guy right here by this, and I divided by that. Now I can integrate. This actually goes back to the example that I did earlier. What's the common mistake here? The common mistake is to do an ln on the left side. But remember, I don't have the correct du. This is the same as the integral of y to the negative 2 dy equals the integral of dx over x minus 1. Now, I don't have any special insight into this, but my guess is that the most common mistake in 2016 on this FRQ was to write ln of y squared. So that integrates to, I use power rule, negative 1, or sorry, I should write it as 1 over negative 1 times y to the negative 1 equals ln absolute value x minus 1 plus a constant. Now, I'm going to rewrite this as negative 1 over y, so the left side looks better, equals ln absolute value x minus 1 plus c. So there are different times for which it makes sense to solve for my initial conditions, or solve for my c, to use my initial conditions to solve for the c. Remember, I wrote that this is the spot, or this is what we use to solve for c. In this case, you kind of want to, well, in general, you want to like kind of look and check and see if it's a good time, right? So, and you need to know your logs for this particular one. But I'm going to kind of just look at these initial conditions. It's x equals 2, y equals 3. And I'm going to ask myself, what happens if I plug that into this? Well, look, the x equals 2 here gives me something that has the ln of 1. And you should know that the ln of 1 is something that we can figure out. So we're going to go ahead and do our initial conditions here. So I'm going to take these guys, and I'll do my work on the side over here. Negative 1 over 3, because y is 3, is equal to ln absolute value of 2 minus 1 plus a constant. So that gives me negative 1/3 equals ln of, 2 minus 1 is 1, so it's already positive, so I don't need to make it positive again. Ln of 1 plus c. Now, you should know that ln of e to the 7th, for example, is just 7. So if we can write that ln, or that 1, as e to the something, then it'll tell me what that something is. Well, you should know that e to the 0 is 1, so we get a 0 there. Or you could just know that ln of 1 is 0. But that gives me negative 1/3 equals 0 plus c. So c is going to be negative 1/3. So my last step is going to be to plug this in, come on, here, combine these two lines with that c value and then solve for y. Because look, up here, I said this in the last video, they asked for the particular solution y equals f of x. They want y to be a function of x. So I need to have just x's, and I need to have y solved for. So if I do this, I get negative 1 over y equals ln of x, ln absolute value x minus 1 minus 1/3. And then this goes back to what I did in the previous video about flipping things, right? If I flip the left side, I get negative y. And if I flip the right side, I get 1 over ln absolute value x minus 1 minus 1/3. And then I can multiply by that negative 1 and get y equals negative 1 over ln absolute value x minus 1 close minus 1/3. Now, in the previous example, in the previous video that I made about this stuff, I didn't like the fraction, so I showed you how to get rid of it. In this scenario, if I was actually doing a free response question, there's no way I would simplify it beyond this. Because remember, AP form works for me, and if this is equivalent to any correct answer, then it's good to go. And if I mess with it to try to do some stuff and I mess something up, then I won't get credit for the work that I had done earlier to get to the correct answer. So if you feel pretty good with this, then you should be able to get all 9 points on this free response question. And I'm actually going to go over to the grading rubric so we can look at it and see how things are scored. Okay, so remember, these things are scored out of 9 points. We'll talk more about FRQs later, but for this one, you get 2 points for part A. You get 1 point for the zero slope, so that's this one, and you get 1 point for the non-zero slope, so that's the remaining 4. And if, like, they're not going to take a ruler and measure to see if this slope is 4. As long as you're pretty close to it, you're good to go. So part B, the tangent line equation. So getting that, they wrote it a little bit differently here, but it's the same. You would get points if you wrote it in point slope form. So you get a point for that. Notice, like, they have the work for this 9. Say you did this dy dx work, and then you made some kind of mistake down here. They don't do half points on the AP. You can't get half a point for the tangent line equation because you did half the work for it. You only get the points at the end, that full point, okay? Second point in part B comes from the approximation. So getting to that 3.9. So let's talk about this, because the AP uses this structure a lot. Oftentimes when they do a free response separation of variables problem, you get your first point for separating the variables. So that was dividing by the y and multiplying by the dx. You get 2 points for the antiderivatives. So you get a point for this antiderivative, so the integration on this side, and you get a point for this. So say, for example, you did an ln over here instead of the power rule, you would get one of those 2 points. Come down here, the constant of integration and uses the initial condition. That's very specific language. They say uses the initial condition. They don't say that you correctly solve for c. So you get a point for doing your plus c and for plugging those values in. Say you did your arithmetic badly and you got c equals negative 1/4 or something like that. They're not going to knock you for that if you use your initial condition and you have a constant of integration. But still, you should be okay with that. You should get that. And then the last one is solves for y. So after you get to this point, if you correctly solve for y, notice their version is a little bit different than mine, but it's still equivalent. So we would all get credit. If you don't use separation of variables, you get no points. And if you don't do a plus c, if you forget your plus c, the maximum you're going to get is 3 out of 5 points. So that's for those first 2. You can't solve for the y and get the points later. Say, for example, you integrated this side with an ln. And then you solved for uc and you got the correct c based on having that ln. And then you solved for y correctly based on having that ln. You would lose a point for this, but they're not going to knock you for this and this, because they don't like to compound errors. The only time they'll knock you for compound errors is if you if the error that you make makes the work that you're doing later easier than it would be otherwise. So hopefully you feel okay with separation of variables, you're ready for some more practice, and that you see how they show up on the FRQs. See you. Thank you.